Welcome to the Deep Dive. We're the show that likes to, journey beneath the surface of the everyday.
Uncovering those hidden engineering marvels.
Exactly. The ones that power our world without us really noticing. Today, think about this. There's this vast network, totally fundamental to our health, our comfort. But it's almost entirely invisible.
You're talking plumbing, right?
I am. We're talking about that silent, intricate labyrinth of pipes hidden behind your walls, under your floors. It's the system that makes our homes, our businesses, our cities just work.
It really is astonishing when you stop and think about the engineering involved. We just turn on a tap, flush a toilet.
And take it completely for granted. But underneath that simplicity, it's incredibly complex, meticulously designed infrastructure.
A real convergence of precision, physics, public health. It's all in there.
Absolutely. And today, we are diving deep into the heart of American plumbing. Specifically, we're focusing on a foundational element, the drain waste vent system, the DWV.
Right. We're going to peel back the layers on how it works, the standards governing its design.
And why it's such a demanding engineering challenge, especially, when you scale it up to multi-story buildings.
And our guide for this. We've meticulously extracted our insights from a truly definitive source. The ASPE Plumbing Engineering Design Handbook, Volume 2, the 2022 edition.
Yeah, this isn't just some textbook. It's the authoritative guide for plumbing engineers in the U.S.
And we're here to distill that wisdom, bring you the critical info, the key principles, maybe a few surprises.
Our mission is pretty straightforward. Give you a shortcut to being well-informed on the critical components, the key American standards, the engineering principles for safe, efficient plumbing here in the States.
We want to demystify the codes, the regulations, the backbone of these essential systems.
So whether you're a mechanical engineer, an MEP designer, a plumbing contractor, maybe a code official,
You should find some valuable nuggets here, maybe a few aha moments about the systems you work with daily.
and even if you're just, technically curious, by the end of this, you'll have a much deeper appreciation for the unseen work of plumbing engineers.
Definitely. It's vital work.
So let's get started. Let's unearth this fascinating topic.
All right.
Okay, first things first. What exactly is a DWV system? It sounds like one thing, but it's really three functions working together, isn't it?
You got it. At its core, a DWV system is the essential gravity drainage network in a building. Its main job isn't just getting wastewater out.
It's about safety, right? Health.
Precisely. Doing it safely, efficiently, and crucially, without letting health hazards back into the building. It's all about preventing disease spread, managing odors, maintaining hygiene.
So it's fundamental public health infrastructure, really.
Yeah.
And the name, DWV. Drain, waste, vent. Can you break those down for us?
Sure. So first, drainage. These are the pipes carrying discharge from your typical fixtures, sinks, showers, tubs, floor drains, the main path for used water leaving.
Okay.
Then there's waste piping. This is specifically for non-sanitary clear water discharge. Think condensate drains from AC units, or maybe discharge from equipment that doesn't handle human waste.
Like indirect waste.
Exactly. Water that needs removing but isn't, sanitary waste.
And then the third part, the vent, often overlooked, but you're saying it's vital.
Absolutely vital. This is where the real genius lies, I think. The vent system is a parallel network of pipes. It runs alongside the drains, usually, but it's not carrying water, it's carrying air.
There, okay.
Yeah, air. And it's critical for managing the air pressure within the entire drainage system. And these three parts, drain, waste, vent, they aren't separate. They work in concert.
They're connected.
Totally interconnected.
Yep.
The drains and waste lines only work properly because the vent system is doing its job, maintaining that air pressure balance. It ensures sanitation, keeps gases out, maintains integrity.
Without all three working together? Probably.
Big problem. Slow drains, gurgling noises, dangerous sewer gas leaks. You name it.
Okay, that makes sense. So with those parts in mind, how does the water actually flow? Especially in those main vertical pipes, the stacks.
Right, the stacks. Well, those main vertical pipes, if they carry waste from toilets and urinals, so human waste, they're called soil stacks.
Soil stacks, okay.
If they're carrying other clear water, like from equipment grains, they're called waste stacks. These are the main highways for the wastewater heading down.
And how does water from, say, a sink get into that stack? Does it just drop in?
No, it's more engineered than that. It enters the vertical stack through a specific drain fitting, usually something like a long-turn TY or a sanitary T.
Those curved fittings you see.
Exactly. They're designed to guide the flow downward smoothly, not just dump it in abruptly. It helps manage the flow dynamics right from the entry point.
And then gravity takes over.
Yeah.
But something interesting happens inside the stack itself, right? It's not just water falling.
This is the really cool part, actually. As the water enters and gravity accelerates it, it doesn't fill the whole pipe like a big slug of water.
No.
No. Pretty quickly, it forms this thin, often spiraling sheet or film that clings to the inside wall of the stack. Surface tension helps with this.
Wow. So it sticks to the sides.
Yeah. And the incredible result is that the entire center of the pipe is left open. It creates an air core.
Air core, running right down the middle of the drain pipe.
Exactly, a dedicated highway for air. And this air core is absolutely vital. Without it, air couldn't move freely to equalize pressure, and you'd get gurgling, slow drainage backups, the works.
Okay, that air core is critical, and that leads us perfectly into traps and vents. We all know that P-trap under the sink. What's its precise job, and how does it connect to this whole venting thing?
Right, the P-trap. Deceptively simple, incredibly important. Its main purpose is to hold a small amount of water, creating a water seal.
A physical barrier.
A physical barrier, literally a plug of water that stops noxious, potentially harmful sewer gases from coming up the drain and into your living space. Methane, other decomposition byproducts, you don't want those inside.
Definitely not. So the trap holds the water seal. How does the vent system protect that seal? You mentioned air pressure.
This is the delicate balance. The vent system is sized and installed specifically to keep the air pressure inside the drain pipes stable, very close to atmospheric pressure.
Why is that so important for the trap?
Well, think about pressure swings. If the pressure in the drain drops too low, becomes negative, like a vacuum, it can literally suck the water right out of the trap.
Siphon it out.
Exactly. That's self-siphonage. Trap seal, gone, sewer gas comes in. Conversely, if the pressure gets too high positive pressure, it can push sewer gas or even wastewater back through the trap into the room.
That's back pressure.
That's back pressure. The vent pipes prevent these extremes. They let the system breathe, equalizing the pressure and keeping that water seal safely in place.
And there's a surprisingly tight tolerance for how much pressure fluctuation is okay, isn't there? It's not just keep it roughly atmospheric.
It's remarkably precise. It is. It shows how sensitive these systems are. The vent pipes, their diameter and their length have to be carefully calculated to stay within this very narrow range. Get it wrong, and you risk siphoning tracks or causing back pressure. It's all about maintaining that delicate equilibrium for the water seals.
Fantastic explanation. Really highlights the hidden engineering.
Yeah.
Okay, now that we've got the fundamentals of how DWV works, let's get into the American standards and design principles.
Yeah.
It sounds like the regulatory side is pretty robust.
Oh, absolutely. And this is critical to understand for anyone working in the field here. For any specific project, the final word, the absolute authority, is the approved local plumbing code.
Not a national standard.
Well, the local code is often based on model codes like the International Plumbing Code, the IPC, or the Uniform Plumbing Code, the UPC, or it might be a local adaptation. But whatever code has been officially adopted in that jurisdiction, that's the rule book you must follow for design and sizing. No exception.
Okay, so the IPC and UPC are like templates, but the local version is law.
Essentially, yes. They ensure consistency and safety across the board.
So then the ASPE handbook we're using, if the local code is king, what's the handbook's role?
That's a great question and a really important distinction. The ASPE handbook, with all its tables and detailed explanations, is there to illustrate and augment the discussion of methods, procedures, design principles. It gives you the why.
The theory, the best practices.
Exactly. The engineering rationale behind what the code requires. But the handbook itself explicitly says its tables and charts are not for actual design use instead of the code. It reinforces that you need to understand the principles, but you design to the code.
Got it. Principles from the handbook, rules from the code. Okay, let's dig into some key American standards then. Horizontal drainage first. How are those pipes designed to keep things moving?
The primary design goal for horizontal drains is for them to flow at about half full capacity under what we call uniform flow conditions.
Half full. Why not full? Seems like you'd get more capacity.
But flowing half full does two crucial things. First, it minimizes those pneumatic pressure fluctuations we talked about. If the pipe flowed full, it acted like a piston, creating pressure surges that could mess with trap seals.
Okay, keeps the air pressure stable. What's the second thing?
Second, and just as important, it helps ensure self-scouring velocity.
Self-scouring velocity. Sounds efficient. What does that mean practically?
It means the wastewater needs to move fast enough to carry solids along with it, preventing them from settling out and causing clogs or fouling the pipe. If it's too slow, solids drop, build up blockage.
Makes sense. Does the source give specific minimum slopes to achieve this?
Interestingly, the ASPE source mentions minimum slopes but doesn't list specific values right there for sanitary drainage. However, the principle of maintaining adequate slope is absolutely paramount for achieving that self-scouring velocity. It's fundamental to the design philosophy.
So it's about designing to prevent clogs from even starting.
Exactly, it's proactive. The historical principle, going way back, is ensuring velocities prevent clogging, fouling, depositing solids. And part of that is also having adequate cleanouts access points built into the system.
Just in case a blockage does happen despite
Yeah.
the design.
Right, you need a way to get in there and clear it. It's a complete approach.
Okay. Now, sizing traps and vents. How do engineers figure out how much pipe capacity is needed for all the different fixtures? Sinks, toilets, showers, everything.
Yeah.
Is there a standard unit?
Yes, absolutely. They use a concept called drainage fixture units, or DFUs.
DFUs.
It's a really clever, standardized way to estimate the probable discharge load on the drainage system. It's based on tons of research and stats about how much water different fixtures use and how often.
So each fixture gets a number.
Yep, each type of fixture has an assigned DFU value. A small bathroom sink might be 1 DFU, a standard toilet might be 4 DFUs, for example. Engineers add up all the DFUs for a section of pipe or a whole building to get a total load.
So you turn random human behavior into a predictable number for calculations.
Pretty much. It allows for accurate sizing of both the drainage pipes and, crucially, the vent pipes.
And speaking of vent sizing, is it the same for all vents? Or does it depend on what the vent is serving?
Oh, it varies quite a bit. A major vent stack serving multiple floors needs to be sized differently than a smaller fixture vent just serving one trap. The size, the diameter, and the length of the vent pipe are critical.
Why both diameter and length?
Because both affect the vent's ability to move air quickly enough to keep the pressure within that tight 1-inch water column limit we discussed.
Yeah.
Too small or too long, and it can't keep up with the pressure changes, potentially compromising trap seals.
Can you give us an example from the handbook, how DFUs translate to pipe size?
Sure. The handbook illustrates this well. For example, if a vent needs to handle 12 DFUs, the minimum diameter might be 1.5 inches. That's 38 millimeters.
Okay.
But if you jump up to a load of 24 DFUs, the minimum vent diameter might need to be 2.5 inches, 64 millimeters, especially if the horizontal run of that vent is relatively short, say less than 45 feet.
Bigger pipe for more load, makes sense. And shorter runs need bigger pipes sometimes.
It seems counterintuitive, but yes, sometimes a shorter, larger vent can dissipate pressure more effectively in certain configurations. It really highlights how diameter and length interact to achieve that precise pressure control needed for the traps.
It's amazing how interconnected and precise it all is. Okay, what about materials? What are DWV pipes typically made of in the U.S.?
For standard DWV applications, you commonly see materials like ABS plastic, PVC plastic, sometimes PVDF, which is another type of plastic, or specific metal pipes like DWV pattern Schedule 40.
Schedule 40, that refers to the wall thickness, right? Yeah.
Exactly. Indicates its pressure rating and robustness. These are typically joined using compression fittings or couplings for a secure seal. And if they're buried, they usually need at least 12 inches, 300 millimeters of cover for protection.
So fairly standard, durable plastics or specific metal pipes for normal waste. But what if it's not normal waste, like corrosive stuff from a lab?
That's where material selection becomes incredibly critical and much more specialized. Standard materials often won't cut it, they degrade fast.
Leading to leaks, failures.
Big problems. So, for highly corrosive wastes, engineers have to specify materials like high silicon cast iron, borosilicate glass, which is like Pyrex, very resistant, or special plastics like polypropylene. Chemical compatibility is key.
You have to match the pipe to the specific waste stream.
Absolutely. You need to know what's going down that drain and choose a material that can handle it long term.
And the source mentioned a really specific, almost shocking hazard with one common chemical waste. Something about explosions.
Yes, sodium azide. It's discharged by some medical blood analyzers. Seem harmless enough in dilution, but if it comes into contact with copper pipes, it can form highly explosive copper azide compounds.
Wow. So you absolutely cannot run that waste through standard copper plumbing.
Absolutely not. In facilities using those analyzers, you must use alternative piping, stainless steel, polypropylene, glass, or have stringent procedures to ensure that azide waste never enters any copper system. It's a stark reminder of how critical material compatibility can be and the potential consequences if it's missed.
Truly startling. Okay, let's touch on floor drains too. Any special considerations there, especially in public or commercial spaces?
Yes, particularly regarding sanitation. Acid-resisting enameled interiors are generally preferred for floor drains over just rough brass or iron castings,
Why enamel?
because the smooth, non-porous surface is much easier to clean and resists the buildup of germs, scum, and debris that can get trapped in the rougher texture of unfinished metal. Better hygiene, worth the extra cost.
Makes sense. Does the enamel affect installation?
It does. You have to use caulked joints when connecting enameled drains. You can't cut standard pipe threads into the enameled metal because the enamel would chip off right where you need the seal. So caulked joints are specified.
Good detail. And safety in public areas. I remember reading about a change driven by shoes.
Haha, yes. Spike heels specifically. Traditional floor drain grates often had openings wide enough to catch a spike heel, causing falls and injuries.
Ouch.
Right. So, especially in public restrooms, corridors, even outdoor decks, you'll often see heel-proof grates now. These typically have much smaller, like quarter-inch, 6.4 millimeters square openings.
Does that reduce drainage capacity?
It can, slightly, yes. But the safety benefit of preventing those trip and fall hazards, particularly in public liability situations, usually outweighs the minor reduction in flow capacity. It's a practical adaptation to a real-world risk.
Incredible how design adapts. Lastly, on specialized bits, the source mentions backwater valves briefly. What's their role?
Backwater valves are crucial safeguards. They're typically installed in drains in basements or lower levels or where the building drain connects to the city sewer.
And they prevent
Sewage backup. During heavy rain or sewer system overloads, the municipal sewer can surcharge, meaning pressure builds up. Without a backwater valve, that sewage could flow backwards up your drain and into your building.
nightmare scenario.
Absolutely. The valve acts like a one-way gate, allows wastewater to flow out, but slams shut automatically if flow tries to reverse from the sewer side. Essential protection against flooding and contamination.
Okay, great overview of the standards and components. Now let's shift to why these DWV systems get so technically demanding, especially when you go vertical multi-story buildings. Managing air and water in those long stacks sounds like a major headache.
It is arguably the core challenge, yeah. It's
Yeah.
a constant negotiation with physics. In tall buildings, you have these really long vertical drops. When water, especially a large slug like from a toilet flush way up high, rushes down that stack
Moves fast. Yeah.
very fast. And as it falls, it creates significant pressure changes in the air inside the stack, both positive pressure below the slug and negative pressure or suction above and around it, like a piston effect.
So that rush of water can mess with fixtures on other floors.
Exactly. The negative pressure, the suction, can pull water out of traps on lower floors as the main flow rushes past. That's the self-siphonage we mentioned. Trap seal broken, gases in.
And the positive pressure?
The falling water compresses the air below it. That positive pressure or back pressure can push gases or even water out of traps on floors below the discharge point. So the whole DWV design in a tall building is this constant fight to prevent both siphonage and back pressure, to keep every single trap seal intact.
Sounds like walking a tightrope. How do engineers actually manage this balancing act across dozens of floors, especially with simultaneous use?
It requires incredibly precise vent design. The sizing of the vents, where they connect to the stacks, how they interconnect,
Yeah.
it all has to be calculated to perfectly balance the air pressure throughout that complex, tall network.
So the vents are constantly supplying air where needed and releasing it where there's excess.
That's the idea. They have to react instantly to discharges happening anywhere in the building, ensuring that even during peak usage, imagine morning rush in a hotel, the pressure never fluctuates enough on any floor to compromise those critical trap seals. It's sophisticated fluid dynamics in action.
Wow. Okay, beyond air and water flow, material selection must get way more complex in tall buildings too, right? Longer runs, more diverse uses.
Definitely. Take thermal expansion. Hot water discharge from laundries, kitchens, even just showers over many floors causes pipes to expand and contract. Over the very long vertical and horizontal runs in a high-rise, this movement is significant.
And if you don't account for it.
Stress on joints, potential leaks, pipe fatigue, even failure. So the design must incorporate expansion joints or loops to safely accommodate that movement. It's a hidden stressor that scales with building height.
And the variety of waste. A mixed-use tower could have apartments, offices, maybe a lab.
Exactly. That diversity is a huge factor. You're not just dealing with standard sanitary waste anymore. You might have acidic lab discharge, caustic cleaning chemicals, industrial process water, each needing potentially different, highly resistant piping materials.
So you might need multiple, completely separate DWV systems within the same building.
Often, yes. One for sanitary, one for lab waste, maybe another for kitchen grease. It dramatically increases the complexity of design, installation, and coordination within the building structure.
Let's talk about some really specialized systems. Vacuum waste systems came up. What makes them so technically demanding?
Vacuum systems are fascinating, often used for ultra-low flush toilets, like 0.5 gallons per flush, saving a lot of water. The demand comes because they don't use gravity primarily. They rely on a constant vacuum maintained throughout the piping network by central pumps.
Usually 12 to 18 inches of mercury, the source said.
Right. It's a significant vacuum. And while horizontal pipes still generally need some slope towards the collection center, the system's power comes from differential pressure. Meaning the vacuum can actually pull the waste slug over obstacles or even uphill for short distances if needed to get around beams or other structures. Something a gravity system could never do. This gives routing flexibility, but requires very careful design and powerful, reliable vacuum generation.
Completely different physics involved. Okay, what about the really hazardous stuff, chemical and radioactive waste? The complexity must skyrocket there.
It's immense. Every detail is critical due to the health and environmental risks. Take the air gap requirement at equipment drains.
That physical break between the fixture and the drain.
Exactly. Must be at least twice the diameter of the drain line. It's a non-negotiable barrier against back siphonage or contamination getting back into the equipment or water supply.
And maintenance. Getting to cleanouts and high ceilings must be tough.
It is. So good design anticipates this. Often, in labs or facilities with high ceilings, the cleanouts are actually extended up to be accessible from the floor above.
Smart. Avoids ladders and lifts for routine access.
Precisely. It's about designing for safety and practicality over the building's whole lifespan.
Are there minimum pipe sizes specified for these hazardous drains?
Yes, often larger than standard sanitary. For example, maybe 2-inch minimum under slab, 4-inch minimum for floor drains in labs to handle spills, and 2-inch minimum for the vents. And the venting strategy is crucial too. Vents typically connect to the top of the horizontal drain line in these systems.
Why the top?
It allows air to escape easily when a slug of liquid flows, preventing pressure buildup. And importantly, it allows air in easily behind the slug, preventing vacuum conditions and ensuring smooth flow.
What about pressurized rooms, like clean rooms? Does that affect the traps?
It does. If a room is pressurized, say, to keep contaminants out, the fixture traps in that room need to be deeper than standard, typically 2 inches deeper than the room's pressurization level.
To ensure the room pressure doesn't just blow the water out of the trap.
Precisely. Maintains that critical seal against the pressure differential.
I've also heard of double containment piping for hazardous waste. What's that?
That's becoming increasingly common, sometimes mandatory. It's basically a pipe within a pipe. The inner pipe carries the hazardous waste. The outer pipe acts as secondary containment.
With leak detection in between.
Usually, yes. If the inner pipe fails, the outer pipe catches the leak, and sensors trigger an alarm. It prevents environmental discharge, adds complexity and cost, but essential for high-risk waste.
And these hazardous systems, even if double contained, can't just join the regular sewer, right?
Absolutely not. Lab waste, radioactive waste. They must be kept completely separate from all other systems until the effluent is treated and neutralized to safe levels according to regulations. This often means entirely parallel plumbing infrastructure, separate pipes, tanks, treatment units.
Huge implications for building design. And for radioactive waste, there's even more. Shielding.
Yes, shielding is critical, using dense materials like lead or concrete around pipes and tanks to block radiation. And the piping itself might need to be routed in a labyrinth pattern.
Maze.
Because radiation travels in straight lines. The twists and turns of a labyrinth prevent radiation from shining directly out through openings or penetrations. It's about maximizing safety through multiple layers of protection. Extremely technical stuff.
It's clear DWV is complex, especially in tall buildings.
Yeah.
But it's not just drains, right? The water supply side, hot and cold, also has unique challenges in high-rises.
Oh, absolutely. They're all interconnected parts of the building's hydraulic systems. For water supply in tall buildings, you almost always need booster pump systems.
To get the water pressure up to the top floors.
Right. And often these systems are zoned. Different pumps serve different floor levels, sometimes with intermediate storage tanks. This helps manage pressure.
How so?
It reduces the static head, the pressure, just from the weight of the water column on the lower floors. Without zoning, the pressure at the bottom of a very tall building could be dangerously high for fixtures. Zoning keeps pressure safe and manageable everywhere.
Makes sense. What about hydropneumatic tanks? Where do they fit in?
Hydropneumatic tanks work with booster pumps. They're pressurized tanks, partly filled with air. They act like a buffer.
A buffer for what?
They can supply water for small demands without the main pumps needing to kick on constantly, saving energy and wear. They also help shave peak demands, providing stored water quickly when lots of fixtures open at once, reducing the instantaneous load on the pumps and mains. Their operation relies on the ideal gas law, how the trapped air compresses and expands.
Like a pressure cushion. And thermal expansion must be big deal for hot water systems in large buildings, too.
Huge deal. Water expands when heated. In a large hot water system spanning many floors, that expansion adds up to a significant volume increase. You must have a properly sized thermal expansion tank. Otherwise, the pressure skyrockets. You'll get nuisance tripping of the water heater's relief valve, or worse, damage to pipes and equipment from overpressure. It's a critical safety component.
And managing incoming city water pressure. It can be pretty high sometimes.
Right. That's where pressure regulating valves, PRVs, are essential. If the incoming pressure is over, say, 80 psi, you need PRVs to reduce it to safe levels for the building's fixtures, usually 40-60 psi.
And they fail.
They can, which is why for critical buildings, parallel installations are often recommended. 2 PRVs side by side. Provides redundancy, one can be serviced while the other keeps supplying water and increases capacity if needed.
Good practice. And finally, that banging sound water hammer. Is that worse in tall buildings?
It can be, yes. Longer pipe runs and potentially higher operating pressures can exacerbate it. That shock wave caused by suddenly stopping flow.
Like closing a faucet quickly.
Exactly, it can be damaging. That's why water hammer arresters are crucial. Their device is installed near quick closing valves.
Won't it work?
They typically have a sealed chamber with compressed air or gas separated from the water by a piston or bellows. When the shock wave hits, the piston bellows moves, compressing the gas, which absorbs the pressure surge. It dampens the shock locally, protecting the whole system and reducing noise.
Essential for system longevity and quiet operation. Wow, what an incredible journey we've taken. From, the simple act of flushing a toilet.
To this incredibly complex, almost invisible network, making it all happen safely and reliably.
We really dove deep into those engineering principles that keep things flowing. The slopes, the vents, the trap seals.
And the huge challenges of multi-story buildings, specialized wastes, pressure management. It's a hidden world of demanding, brilliant solutions.
It really is. And seeing how American plumbing standards like the IPC and UPC provide that framework, it's like an unseen symphony.
A symphony of gravity, pressure, fluid dynamics, material science, all orchestrated for public health and safety. It's meticulous engineering.
And it impacts public health, safety, the environment, in ways we just don't think about day to day.
It's truly a cornerstone of modern life, operating silently in the background.
So maybe next time you turn on a faucet or flush a toilet or just hear water moving in the walls, pause for a second.
Consider that intricate dance of physics, chemistry, engineering, all working perfectly.
It's a hidden marvel we interact with constantly. Makes you wonder.
What other hidden engineering marvels are all around us, just quietly making our lives work? Always more to learn, always more to appreciate.